We welcome all our guests and subscribers of the BeepToolkit platform channel. Our next issue offers you to familiarize yourself with such important disciplines in projects in relation to the platform as universal modular design in hardware with examples of instructions for managing these modules. As a result of viewing, you will come to understand the simple principles of selecting modular components, and will be able to independently develop your ideas from prototyping to industrial designs or final working solutions. All electronic components considered here with their parameters are referenced in the description. Let's start with a simple example of controlling a bipolar stepper motor, which is widely used both in industry and in applied fields. There are a great many detailed videos about this type of engine, and if you are not familiar with them yet, it will not be difficult for you to find detailed reviews about them yourself and recommendations for the correct selection and settings. We took an inexpensive engine and a driver suitable for it, purely for demonstration. Next, we need a 4-channel MOSFET module with galvanic separation of the control power supply and the load power supply. This module allows you to efficiently switch not only power equipment, but also all kinds of logic sensors, which is very convenient, safe for control signal circuits, and advantageous for organizing power from a single DC voltage source, in our case, for 12 volts. At the same time, we can supply logical signal levels to its input channels and output channels from GPIO or various sensors, with power ranging from as much as 3 whole and 3/10 to 5 volts. It is important to take into account that in our case, all controls from the key side on the output channels occur with the opening of the logic levels on the negative voltage potential. In this case, all positive terminals at the input of the MOSFET kit must be shorted to each other and connected to the positive potential of the VC. This type of control refers to a PNP distribution. If the positive potential opens the logical level, then this type of control refers to NPN distribution. But it will not work for us. How we do this, we will demonstrate it to you. But that's not all. An important component in the stepper motor control, along with its driver, is the module of the pulse width modulation signal generator, or PWM. This module is connected to the motor driver and is needed to create a sequence of pulses where each pulse is one step of the motor. The frequency of these pulses determines the speed of rotation of the engine. In case of termination of the PWM signal, the motor enters the shaft holding state. For this purpose, we chose such an inexpensive but very convenient module that allows you to visually monitor and configure the chat supplied to the driver in the range from 1 Hz to 150 kHz and the duty cycle via an LCD display. The convenience of this module also lies in the fact that it is powered by a constant voltage in the range from 3 whole and 3/10 volts to 30 volts. The module remembers all the entered parameters, and there is no need to reconfigure them. Now it remains for us to place on the stand a 12-volt DC unit with a supply of up to 5 amperes, a USB GPS module with 16 output channels, and a USB hub. Thus, all modules are assembled, and it is possible to proceed to their connections in the logical control scheme. Let's do it. This is what our first scheme looks like. Logical commands will be sent to the input channels of the 4-channel MOSFET module from the BeepToolkit software controller via an external USB 16-channel output module. For those who are just on the threshold of entering the world of binary logic, we remind you that all the logic of commands, such as opening certain output channels with a logical unit, is equivalent to pressing the button to the on position and holding it. Repeated access to the channel with a logical unit translates the channel state to 0. And this is equivalent to releasing the button to the off position. This state of the signal is also called a trigger state. The sequence of your actions is the first, we supply a total power supply of 12 volts. Second, activate the USB GPIO in the output kit. In this case, the USB hub we use, after the computer determines the connected new USB device, gives an indication in the form of red and blue LEDs, which indicates that the power supply of the device and data exchange with the computer are present. Third, run the BeepToolkit and determine, and if necessary, configure the GPIO ID number of the output device. To do this, by pressing the button of one of the unused channels, we must visually track the flashing of the red LED on the GPIO. If there is no flashing, you should switch to another number in the ID out field until testing gives a positive result. The software and hardware status of the channels is monitored by the LEDs in this location. After the settings, all channels should be set to the state of the program control algorithm. Pressing the number 1 button starts the engine, pressing it again stops the engine. At the hardware level, it works like this. When GPIO channel number 1 appears at the output, the logical signal level of 5 volts opens. This signal is fed to the first channel of the MOSFET switch, which opens up 12 volts of power at its output, towards the motor driver and the PUM generator, which are physically connected in parallel. The motor rotates counterclockwise. Blue LEDs indicate the presence of a 12-volt power supply at the power terminals of the switch. Pressing button 1 again closes the GPIO output channel number 1, the off state. Accordingly, the MOSFET switch is switched off by powering the driver and the PUM generator. The engine stops. We proceed to our stand and perform all the actions. We determine the device identification number. It is defined as the second one. Click on the 1 button. As we see, the problem has been solved. Let's complicate the algorithm and build a stepper motor control scenario using the following algorithm. From the moment the script starts, the engine rotates counterclockwise for 5 seconds and stops for 3 seconds, after which it starts again in the same direction and stops after 3 seconds. To execute such a scenario, we need to go to the scripting console and enter instructions for the accepted algorithm. To work with scripts on the panel, we will specify the GPIO ID number for working from the 1st to the 48th port, which, if necessary, will allow us to organize access to the specified device on 48 ports. Also, a prerequisite for the operation of the BeepToolkit with scenarios is the mandatory connection of the input USB GPS kit for 10 or 16 channels. By default, the system is configured to work with a 10-channel module, but at this stage, we are not considering working with the input kit. The script console on each tab contains 16 configurable ports. Let's enter the instructions we need. So, port number 1 will open instead of the number 1 button with the same channel number as the button, but in automatic mode from the moment the script starts. It will open instantly, so in the timing field, we do not set the time of its opening start. Also, by default, we have specified the operation of the port with a 10-channel module and its USBCOM ID number, in case we work with the input channels of the channel of this kit. Port E, according to the scenario, will count down 5 seconds, during which the engine will run and stop. Port 3 is set to pause for a time of 3 seconds, after which the engine starts again. Port 4 counts down the engine running time for 3 seconds and stops it. All other ports that are in the if state do not participate in the script, except for the is port, which is always final, and must be active in order to complete the state polling of all ports. One of the important functions is the ability to save scripts and all settings as their libraries in the form of binary files, which in the future will allow you to quickly access them for quick entry of port instructions. Such scripts can be changed and saved under other names or transferred to other users for further work with them. In the BeepToolkit environment, assign the name test1 and save it. To run it, we will enter a client key, part of which is generated by the software kernel. And the other part is a personal password that is provided to users during the licensing process. Launching. During the execution, we monitor the transitions between active ports on the digital display. This is a very convenient function that allows monitoring of long chains of scenarios and, if necessary, to fix one or another port by number to change its instructions. In addition, we have the ability to run the entered script repeatedly with cyclic repetitions, the number of which is entered in this field. We can also arrange for the script to run automatically from the moment the BeepToolkit is loaded. Such a countdown is set in this field. At the same time, the wait button should be switched to the state during the input of instructions. In the process of executing such an instruction with a global timer, BeepToolkit, upon completion of all tasks, is unloaded, with a complete shutdown of the computer. By default, this function is in a waiting state when BeepToolkit is loaded, which does not lead to a complete shutdown when any scripts are completed. Now let's move from simple algorithms to more complex ones and make our engine work according to the scenario, with a reverse or a change in the direction of rotation. The scenario is as follows. After starting the engine with counterclockwise rotation for 5 seconds, the engine stops for 3 seconds. And starts in the opposite direction with work for 5 seconds, after which it stops for 5 seconds. And starts again in the same direction with work for 5 seconds with a stop. For this control, we will need to make changes to the module connection scheme. To switch to the reverse mode of the motor to its driver, a voltage of 12 volts must be applied to certain terminals with the designation Q and Q+, as shown in the diagram. Also, to run this mode, we will need additional logical control from the BeepToolkit. Output channel 2 will be responsible for starting the reverse. When it is open, the motor changes the direction of rotation. When it is closed, there is a change in the direction of rotation in the opposite direction. Thus, the second channel will supply a voltage of 12 volts to the corresponding terminals of the driver. At the same time, in the intervals of pauses, its shaft is free from retention. In the event that we need this application of the shaft retention mode at the moment of its shutdown, in this case, an additional output channel is required for independent control of the PUM generator. At the same time, it is necessary to exclude it from parallel connection to the power supply by the engine driver. We proceed to test hardware tests. We save this script under the name test2. Launching. Everything works in strict accordance with our algorithm. Now that we have demonstrated how the platform works with logical instructions and hardware modular design for working with output signals, let's move on to the most interesting part of the toolkit's capabilities. This is feedback automation. When sensors are present in the hardware design, that will read the control signals of the devices. For this work, we will need a USB input kit for 10 or 16 data acquisition channels. This module reads the voltage supplied to each channel in the range from 0 to 3 whole and 3/10 of volts. This module is connected to a USB hub and has a converter with 5 to 3 whole and 3/10 of volts on board. And this power supply can be used for the reference power supply of converting MOSFET modules. Direct connection to higher voltages may cause the module to fail. The module can also read the above voltages from other more powerful sources. But we'll talk about this a little later. And for those who are interested in more detailed information, you can go to their description below by following the links. The circuit includes induction NPN position sensors powered by 12 volts and the familiar stepper motors with their drivers, and PUM generator modules. There are also modules of logic MOSFETs of switches with galvanic isolation according to signal and power voltages. One of the engines is equipped with a screw shaft, along which the carriage will move along its axis. Unlike the previous schemes that were discussed here, the sensors will register the aluminum flags of the movable carriage, according to its extreme positions. The input module will read this data and transmit it to the BeepToolkit. The values of these voltages will be taken as trigger commands instead of buttons and control the output channels. The behavior of stepper motors. Let's consider an example of an algorithm for control. From the moment the script starts, the screw shaft engine starts and moves the carriage along its axis to the rightmost position. After that, the direction of movement of the carriage changes to the opposite and it moves in the opposite direction. At the same time, from the moment the carriage starts moving, the second engine starts counterclockwise for 3 seconds and stops waiting until the carriage reaches its original position with a stop. At the same time, the second engine resumes clockwise rotation for 5 seconds and stops. Here's what the instructions of our algorithm look like. For this control, we will need 10 BeepToolkit ports, which will be configured to work with 4 output and 2 input channels of USB GPIO modules. Let's use the panel to test the position sensors and the absence of errors in their hardware connection. Specify the ID COM port of the input module and note the sensor numbers 1 and 2. In the absence of metal flags in the sensor response zone, there is no readable voltage, and when accessing them, the 16-channel display displays 0 volts on these channels. If a metal flag is brought alternately to the sensors, then the read voltage will be in the range of 2 to 3 and 3 volts. It is on these values that we will enter the trigger conditions. Such values are called trigger variables. So, if the trigger value exceeds 1 volt, it is true, and at the same time conditions for executing the necessary logical commands. The first port, via the third output channel, simultaneously supplies 12 volts of power to the stepper motor driver with a screw shaft and to the PUM generator module, which leads the carriage to move linearly along the shaft to the opposite point. The second port is in standby mode with a timer of 1 minute, during which an event should occur to trigger the second position sensor. And when he fixes the presence of a metal flag in his zone, a logical trigger will occur to open output channel 4, which will open 12 volts of power to the driver to reverse the engine in the opposite direction, and the carriage will move towards the first position sensor. According to the scenario, the third port starts the stepper motor counterclockwise with the second ball, while the carriage continues to move. The fourth port, after 3 seconds of operation of the second engine, disables its driver and PUM generator. The fifth port, at the moment when the carriage of the first position sensor reaches, receives a trigger value 4, closing the output fourth channel of the reverse switching. In this case, the carriage begins to move in the opposite direction. The sixth port closes the third output channel, and thus the engine stops at the start point. The seventh port supplies 12 volts of power to the second output channels to reverse the first engine. The 8th port, via the first output channel, supplies 12 volts of power to the driver and the pump generator of the first motor. To start it with a clockwise rotation of the shaft, the 9th port waits 4 or 5 seconds, and the first channel turns off the power to the driver and the pump generator, as a result of which the first motor stops. The 10th port switches the second output channel to the off state and turns off the power to the reverse driver of the first motor. In the end, the entire power part of the circuit is de-energized. Now we move on to the most important thing, live testing, with full involvement of both output and input channels, and feedback from sensors. Monitoring plays a key role here. A 16-channel voltmeter monitors when and which sensors are triggered. This will help to make sure that trigger variables are processed correctly. That is, a value greater than 1 volt really triggers the necessary actions. A 3-segment digital display clearly shows which port is currently in the active phase of script execution. This greatly simplifies debugging, especially if you are working with more than 10 steps. It is important to monitor during the tests whether there are reaction delays between the triggering of sensors and logical actions at the hardware level. For example, the shape and size of metal flags, depending on the speed of their movement in the sensor range, can affect the speed of their operation. Make sure that all the conditions of the scenario are met, strictly according to time and signals, without omissions. Check the stability of the operation when the script is cycled, if it is enabled. If everything works fine after the first run, it's a good sign that the scripting architecture and hardware design are done correctly. Upon completion of the test, we can save its instructions and parametric communication settings in the script library. For further work on the project, or apply these instructions for the following ideas. Let's start. BeepToolkit is the shortest way from an idea to a working prototype and then to an industrial model. Without coding, without unnecessary confusion, with maximum visibility. You control the hardware directly and immediately see the result. This is not just a demonstration, it is your first step to understanding the world of binary logic, to creating real projects in the field of automation and robotics. We will be grateful for your feedback, comments, and questions. Share this video with your friends and colleagues. Your opinion and feedback are really important. Thanks for watching, and see you soon.